Think about every road you've ever driven on, every single bridge you've crossed, and honestly, almost every building you've ever set foot inside. They all share one incredibly unassuming gray foundation: concrete. We rarely give it a second thought, but the world produces so much of this stuff every single year that the scale is almost impossible to wrap your head around. Imagine, just for a second, taking all the concrete produced globally in a single year and pouring it into one massive river. That river would start way up at the Arctic Circle and stretch all the way down to the very southern tip of South America. It's actually the second most used resource on Earth. The only thing we humans consume more of is water. More than oil, more than steel, more than wood.
To put that demand into perspective, get a load of this. Between 2011 and 2013, China used more cement, which is the binding ingredient in concrete, than the United States used during the entire 20th century. And no, that's not in a generation or a decade, that was in exactly 2 years. In that tiny window, whole megacities were just built from scratch, and huge highways connected totally untouched regions. The global appetite for this material is just staggering, and practically every crane, every blueprint, and every building code out there assumes that traditional concrete is really the only way forward. But what if everything we thought we knew about building the modern world was about to change? Welcome to This Explainer. Today, we're diving into a massive structural shift that's happening right now in global construction. We're going to explore exactly how decades of deeply ingrained engineering norms are being completely flipped on their head by a couple of deceptively simple yet absolutely groundbreaking innovations.
So, here's our roadmap for today. We'll start with the concrete climate crisis, followed by the chemistry of cement. Then we'll get into the compression casting revolution and B-Core, the steel alternative. Finally, we'll look at the global economic shift and the challenges for the future.
All right, part one, the concrete climate crisis. Hiding in plain sight inside practically every modern structure is an invisible environmental monster: 8%. That is the chunk of all human-made greenhouse gas emissions worldwide that the cement industry alone is responsible for. Let that sink in for a minute. That is more than the entire global aviation industry combined. It's actually almost as much as all the cars and trucks on every road on the planet. For decades, scientists have known this is a catastrophic problem. But fixing it, that's proven to be an absolute nightmare.
Which brings us to part two, the chemistry of cement.
To really understand why this is such a stubborn issue to solve, we have to look past the construction sites and peer directly into the chemistry itself. You see, the trap isn't just about using dirty energy to run factories. To make cement, you literally have to heat limestone to over 1,400 degrees Celsius. And when you do that, the rock breaks down and physically releases carbon dioxide directly as part of the chemical reaction. So even if every single cement factory on Earth ran on 100% clean, renewable solar or wind energy tomorrow, we'd still be generating massive amounts of CO2. Why? Simply because it's a mandatory part of the recipe. The carbon is literally baked right into the chemistry.
Moving on to part three, the compression casting revolution. So back in 2025, there was this massive aha moment. A team of Chinese researchers published a study that completely challenged a century of assumptions about how we treat this material. For generations, the core process of making concrete has been exactly the same. You mix the ingredients, you pour it into a mold, and you wait. You just let gravity and time do the work while it slowly cures and hardens. But this team asked a totally different question. They asked, what if the problem isn't what we put into the concrete, but what we do to it the moment it leaves the mixer? Instead of just passively waiting around, they decided to intervene immediately using a method called compression casting. Okay, let's break this process down because its simplicity is just beautiful. While the newly mixed concrete is still fresh, wet, and malleable, they apply immense pressure to it, somewhere between 5 and 15 megapascals. To give you an idea, that's like the force of a heavy industrial hydraulic press. Think of the wet concrete almost like a sponge. By squeezing it hard from the outside in, they force out the excess water and any trapped air bubbles. The particles get packed super tightly together. This completely transforms the internal structure from a loose, wet mixture into a highly dense, incredibly robust block in a matter of moments. And the data on this, it is absolutely wild. Porosity, which are those tiny little hollow spaces where water, salt, and chemicals usually seep in to rust the internal steel, dropped by 45%. The overall compressive strength shot up by over 85%. But the most crucial metric is that last one, boundary layer voids. See, in traditional concrete, the weakest link is the microscopic border where the cement paste meets the gravel. That is exactly where cracks always start. Well, compression casting reduced the voids in those exact boundary layers by 35%. They basically fortified the weakest link in the entire chain, and they did it using the exact same traditional ingredients. No expensive new additives, just pure physics.
Now, in a highly secretive industry where new formulas are fiercely guarded behind patents and corporate firewalls, these researchers did the unthinkable. They published everything for free. We're talking raw data, extreme magnification microscopic images, nanoscale mechanical tests, the whole shebang. This radical transparency completely shocked the industry. It sparked an absolute firestorm because it allowed engineers worldwide to just download the data, immediately test it out in their own labs, and verify these astonishing results for themselves.
Part 4. B-Core, the steel alternative. So while those scientists were fixing the chemistry of concrete, another group was out there asking if we even need to use so much of it in the first place. Enter B-Core. Developed by the Broad Group, this is a structural system inspired directly by aerospace engineering. Instead of relying on these thick, heavy slabs of concrete, B-Core uses two extremely thin steel plates. Sandwiched between them is a highly precise network of hollow steel tubes. Imagine a giant, incredibly precise steel waffle iron. Think about it. Airplanes aren't strong because they're heavy. They're strong because they distribute weight intelligently. B-Core uses that exact same logic, but for buildings. A B-Core structural element actually weighs less than 1/10 of a comparable reinforced concrete slab, yet it can carry similar loads. And because it's so incredibly light, it completely changes the game for earthquake resistance. When an earthquake hits, a heavy concrete building absorbs massive amounts of force, simply because it has so much mass. But a B-Core building, being intensely lighter, flexes and distributes those shockwaves rather than fighting them. It makes it drastically safer in seismic zones. Beyond just the safety aspect, the speed of assembly is mind-bending. B-Core operates almost like giant self-assembly furniture. The panels connect together perfectly with robot-assisted joints that require absolutely no special tools. In 2025, a 10-story building using these modules was assembled in Chengdu in less than 30 hours. And the crazy part? The workers weren't even rushing to set a record. The entire system is just engineered from the ground up to go together fast, clean, and perfectly every time. Let's look at Part 5, a global economic shift. So we have vastly better concrete and a system that requires way less of it. Now let's step out of the lab and look at the massive global economic ripple effect this is causing. Normally, the construction industry takes decades to adopt a new idea. But by 2026, literally just a year after that initial open source research, Holcim, one of the largest cement manufacturers on Earth, signed a 5-year licensing deal. Over in Germany, a research consortium began testing compression casting on a real Autobahn project near Berlin. In Japan, Obayashi Corporation initiated programs to slash their cement use for the Osaka Expo. This isn't just academic curiosity anymore. We are watching a real-world gold rush. And the real-world tests, the praxis tests, are proving the economics for sure. Take the Pinjiang River, for instance. A 150-meter bridge deck built with compression casting, hitting 61 megapascals of strength, was monitored 24/7 for an entire year. The result? 0 visible cracks and perfectly stable moisture levels. In Shanghai, a residential pilot project showed 15% better insulation and far fewer repairs. This global shift is definitely not being driven by green marketing campaigns. It's driven by pure, undeniable economics. The product is stronger, it lasts longer, and there are currently 34 international patent families betting real money on it. Plus, we're seeing huge market movements, like China exporting 124 million tons of related additives in 2026 alone. Finally, Part 6, Challenges for the Future. Now, to truly understand the scope of this shift, we have to ground our excitement just a bit and look at the very real hurdles standing in the way of rewriting the world's infrastructure blueprint. The science is brilliant, yes, but global building codes are intentionally slow to change. If a structural component fails, people can die. Because of this, every single country has to validate these new methods against their own strict safety regulations, using their own local materials and specific climates. On top of that, upgrading thousands of existing concrete plants to accommodate compression casting machinery requires massive upfront capital. For wealthy nations, this pays off quickly, but for smaller companies and developing nations, those initial economic barriers can be incredibly steep. Yet the prize at the finish line is monumental. Current models suggest that if just 30% of the world's newly poured structural concrete utilized compression casting, we could reduce annual CO2 emissions by 850 million tons. That single change, applied to less than a third of the market, would save more carbon dioxide than the entire nation of Germany emits in a full year, across all its factories, cars, and power plants. We've seen how squeezing the air out of wet rock and borrowing ideas from airplane wings can fundamentally alter the trajectory of human emissions. But I want to leave you with this thought. If an idea as simple as applying pressure to wet concrete lay hidden in plain sight for decades, right in front of millions of engineers, what other massive, world-altering breakthroughs are currently sitting right under our noses, completely undiscovered?